Hello everyone and welcome back to a new video in our modeling, analysis and design of pile foundations. We are still in the theory part of pile foundations because I want to finish the entire theory part before we explain this in Robot, because you cannot do anything in Robot without understanding the theory behind piles. Now this is part of a video series that will be linking at the top right, so if you are new to this channel, please take a look on the video series so that you can catch up with everything I've talked about before. Now in this video we are going to start talking about the skin resistance. Now, I wrote two objectives, but I found that sand is a big chunk, so I'm not going to talk about clay today. So I'm only going to limit my talk about sand today. We are talking about the skin resistance, so skin friction of the pile on the soil, and it's part of the total capacity, because the total capacity of a pile is going to be the tip bearing capacity and the skin friction. So with that being said, without further ado, sit back, relax, and enjoy the show. Alright, now before I start, I want to go back to the basics of physics. If you have a block moving on a rough surface, then there is friction. And the amount of friction depends on the reaction N and mu. So the friction force usually is mu, a friction coefficient, multiplied by N. Now I want you to take this entire picture and rotate it 90 degrees to reach the friction of a pile. If you have a pile on the right side, then the amount of friction resistance on the pile depends on the normal force on the pile, which is the lateral force of the soil, the clamping force, and the friction coefficient that depends on the soil characteristics. So basically what I'm saying here is that the friction is going to be the lateral pressure multiplied by the friction coefficient, based on physics, because you know that the friction force is N multiplied by mu. So N here is the clamping force, which in soil is called the lateral pressure, because if you have pressure vertically on a soil, you will produce the lateral pressure based on something called the lateral pressure coefficients. There is active, passive, and at rest. So this K is needed for the lateral pressure, which is N in our function or equation. And then we need to multiply it by mu, the friction coefficient, to find the friction force. So our objective now is, I need to find the lateral pressure coefficient and I need to find mu. Now there is more to that, and I will talk about what there is in a moment. But for now, let's just focus on K and mu. Well, mu is tan delta. Now you can notice that there is no phi here, it's a delta. And we will talk about them step by step in a moment. So basically, from physics, this K sigma is the clamping force or the normal force N, and tan delta is the friction coefficient. Now, of course, delta here is the friction angle, but not between the soil and soil particles, but between the soil and pile. It's different from, but related to, the friction angle. QS in the end is going to be the summation of P delta L F. Because the lateral pressure changes, the friction resistance changes. So you could integrate the entire thing, or you could just do it piece by piece and calculate the friction resistance of every single piece. This is what is being done here. Now, of course, it doesn't answer the question, and it doesn't even talk about the complexity of this thing. Because as you have seen, it seems that the friction resistance increases up to a certain point and then remains constant. Now, this point here is basically a cutoff point where the friction resistance doesn't increase, and it's usually at 15 diameters. Now it's between 15 and 20 diameters, but usually we take it as 15 diameters. So up until 15 diameters, the friction increases, and then the friction just doesn't increase at all. So that's the first thing I want to talk about. The second thing I want to talk about here is that, well, if you have driven piles, then you are driving or forcing the pile in, which causes vibration, which causes soil densification, which is a good thing. Because when you drive a pile in, the soil becomes distorted because it must open up for the pile that is being inserted, which causes soil densification in the region around the pile, which is a good thing usually. And the friction factor depends on the soil densification. High displacement methods have a higher friction than low displacement methods, which in turn have a higher displacement than board piles. To finalize this, for Z equals 0 to this transition, you have an increase in the friction angle, in the friction coefficient. Afterwards, the friction just doesn't change. How can I find the lateral earth pressure K? Brajamdas' book says basically that the K factor changes from position to position on the pile. It's approximately equal to the passive ranking pressure at the top of the pile and becomes a little bit less than the coefficient at rest in the bottom. The recommendation here is to use those equations for the K value. And you can see that K value is assumed to be approximately at rest for a conservative approximation. There is also Mansour and Hunter from 1970s that tell you that here are the magic numbers for, I don't know, like piles. I'm kind of a fan of this because it takes the soil characteristics into equation, because this is kind of odd because I don't know exactly what the soil is. So I'm a fan of this one. We still need also to know what the soil to pile friction is. Now, if you remember from your foundation engineering, it was taken to be 2/3 in retaining walls. This was done, I think it was in Braja's book. I remember that from years ago, where we use the friction angle of 2/3 phi to estimate the friction between the soil and the retaining wall. Now, this is not a retaining wall, so it's a little bit different, but the range still stands, like it's between 0.5 and 0.8, so 66% is actually well within the range. Now, that's not the only source, because you can see that, for example, in Kulhawi 1984, wait, before I continue, you think that this science is ancient, and it is, to be honest, and those are the pioneers who used field tests to estimate things. Now, everything is solved via finite element methods, so it's kind of different. Anyway, it tells you that if you have some sort of pile material, you can estimate the soil to pile friction to be a ratio of the soil friction angle. So what I'm saying is that those values are not set in stone, and that's one of the major approximations you have. You can always go to the conservative and say half phi, but of course, sometimes you can become over-conservative. So this is basically the stratified way of finding the friction. Now, some scientists thought that this is a little bit too much. And what about we just, like, instead of doing this stratified approach in the skin resistance, let's just assume that the skin resistance is constant on the entire pile. Now, if you assume that the skin resistance is constant on the entire pile, then the full side area multiplied by this average friction is going to be your skin resistance. And this is the next set or family of equations to estimate the skin resistance. So this family of skin resistance equations uses one average friction for the entire length of the pile. QS in this case equals friction average multiplied by the perimeter multiplied by the length of the pile. Once again, we have Coyle and Castello's method, which says function average equals K sigma tan. Remember that sigma in Coyle and Castello is the average between the vertical sigma and two sigmas from the left and from the right. Also notice that Castello here assumes 0.8 for the delta. How can I find K? Easy enough. Since we're talking about CC, you will have a function here or a graph here where you apply the embedment length and get out your coefficient. Pretty easy enough. Of course, if you have F average, then multiply by perimeter and length, and you're good to go. There are other functions like the standard penetration test. For driven pile, it's 0.02 atmospheric pressure and 60 average. And for low displacement piles, it's smaller, and Broad suggested a different method. The PA here is the atmospheric pressure, and N60 here, this is very important to notice. It is the average on the entire length of the pile, on the entire length, not just the end. Because if you remember, there was one equation that finds the tip bearing capacity, and in that equation, it tells you use the SPT for 10 pile diameters on top and 4 pile diameters on bottom. This was the only localized region for the averaging for the tip bearing capacity, and this was discussed in the previous video, which I'll be linking on the top right. Since we are talking about the skin resistance, it's no longer the tip region, it's the full length of the pile, and that's why the SPT test is taken for the full length of the pile. Alright, there's an example I want to talk here about very quickly. You want to find the skin resistance for a given pile. It tells you that you have a concrete pile, such and such, it's a rectangle, and it's in sand. Notice that all the equations are relying on having homogeneous soil, so a stratified soil is a crazy thing to do. The pile is 15.2 meters long, and those are the variations of N60. Those are the SPT tests taken at every depth of those depths. Now, since our pile is at 15.2, you would need to take all those SPT tests if you want to estimate the skin friction resistance. If you want to estimate the tip bearing capacity, you would need, I don't know exactly how much, but I think you would need those values or something, maybe those. So like 10 diameters on top and 4 diameters on bottom. Not sure, but I just estimated something very quickly. So let's take a look on how he solves it. First of all, he finds the average and 60 for the entire length of the bar. And notice that 16 is not taken because 15.2, like there is no need to take the 16.5. So he averages them into 14.7, so 15. Now, 15 is, I mean, if, I don't know, I usually like to be conservative, so I would take 14.5 or something. All right, now if you use Meyerhoff's method, and we are assuming that the pile is driven, then, wait, is it given? It's not given if it's driven, but I'll assume it's driven. So 0.02 PA and 60 gives you this for skin friction. If you multiply it by the total area, which is the perimeter multiplied by the length, you get the total skin resistance. From broad, you get this value, which will give you this. You can notice something, you can notice a trend here. Like this is a big difference, right? Now, here's the thing. The skin resistance in Meyerhoff seems to be underestimated, and in Briard, it seems to be overestimated. Now, let me tell you something. The tip resistance for that pile, from example 11.3567, was found to be those values. Notice that Meyerhoff overestimates the tip bearing capacity, but underestimates the skin friction. And Briard overestimates the skin friction and underestimates the bearing capacity. If you add them together for Meyerhoff and for Briard and use a factor of safety of 3, you will get something around each other. I once again disagree with Braja's assumption here, or I disagree with Braja's conclusion here. Dear Professor Braja assumes an allowable pile capacity to be taken around 490. I would go with 480, to be honest. I would go with the smaller values. I took a screenshot here just to tell you that sometimes I do disagree with Braja Mdas's book. So in my case, I would take a 480 to be a little bit more on the safe side. Remember that the total bearing capacity of a pile is the tip bearing capacity and the skin resistance divided by the friction, by the factor of safety. So yeah, that is everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a skin resistance sized shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on. Especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.